So the way that the energy is deposited over a given distance is defined in terms of the linear energy transfer, or LET. Basically, um, this is the energy transferred per unit length of the particle track, right? So the distance over which the particle is traveling. The units of this are kilo electron volts deposited per micrometer. And in terms of the types of particles, some, for example, like photons, can have a very low probability of interacting with the material. And so they have a low LET. Whereas alpha particles, for example, or neutrons, are very heavy and have a very high probability of interacting with the material. And so these are very high LET particles. Now here's an example of what that might look like. So on the left is a low LET particle coming in and causing ionizations or excitations, and the electrons or photons that are scattered can go on and interact with other parts of the material. However, these interactions are spread out over a relatively large distance. Now contrast this with the image on the right. An alpha particle comes in and has lots and lots of interactions, lots of those ionizations and excitations, all along the track of the particle in a very highly dense region. And this is the high LET. So here's a table of different LETs for different types of radiations. Highly ionizing particles, like the alpha particles and neutrons, have appreciable mass and sometimes charge too, and therefore a greater probability of interacting with matter. Hence the reason for their high LETs. Now, in terms of the LET, it can be calculated in different ways. The track average is calculated by dividing the track into equal lengths, equal distances, and averaging the energy deposited in each length. However, you can also calculate it using an energy average, which is basically dividing the track into equal energy intervals and then averaging the length of the track that contain this amount of energy. While it has been argued that this has less effect on low energy X-rays or electrons, the track average and energy average can be quite different for high energy neutrons. For example, 14 megaelectron volt neutrons have a track average of 12 kiloelectron volts per micrometer, but an energy average of 125 kilovolts per micrometer. Here's some examples of LETs averaged over track length or energy. The differences in rates of energy loss for the different LETs will produce different degrees of damage. In other words, equal doses of radiation in different LETs do not produce the same biological response. And we've been talking about units of grays that represent the amount or dose of radiation absorbed. Coming back now to the biological effect, equal doses do not cause equal biological effects. And so what that basically means is that 1 gray of neutrons produces a greater biological effect than 1 gray of X-rays because of their high LET deposition. Now, the National Bureau of Standards define the relative biological effectiveness, or RBE, in 1954 to be the dose from 250 kiloelectron volts X-rays relative to the dose from another type of radiation that might cause the same kind of biological effect. For example, imagine we are looking at the LD50, which is the mean lethal dose. If for 250 kiloelectron volt X-rays, we define LD50 as 6 grays, but for neutrons, the LD50 is only 4 grays, then the RBE is the ratio of 6 to 4, or the value of 1.5. Now, RBE is not the same for a given radiation, and depends on dose and the biological effect that's being compared. Alternatively, instead of looking at LD50, we can just look at the survival curves. The survival curve for X-rays has a larger initial shoulder, but for fast neutrons, the shoulder is much smaller. To appreciate the shape of the curve, we have to consider the stochastic nature of energy deposition. For high LET, a cell may only require one hit to be killed, as the radiation can cause significant localized damage, and therefore cell death will be linearly dependent on dose. However, for low LET, different radiation interactions may be required. In other words, 2 separate breaks in the chromosome may be required for the radiation damage to be lethal to the cell. We'll come back to this a little bit later. The upshot is that because the survival curves have different shapes, the relative biological effectiveness, the RBE, of a given radiation source does not have a unique value, but can vary with dose, often getting larger as the size of the dose is reduced. Let's talk a little bit more about the cellular targets that are being hit by the radiation. Recall that target should not be interpreted as being a selective interaction with any particular place in the cell. Radiation always acts randomly. Instead, a target is an area where ionization will have a greater consequence on the cell. Since DNA is the molecule in the nucleus that controls all cellular activities, this is the most likely target for radiation action. Let's look at the different ways in which radiation can damage DNA.